Hey everyone and welcome back to my channel. So today we'll start the second part of this lecture 4, that is on control units. So up until now we have learned what does a control unit do, what is a control signal, what is a control word, and we have learned about one type of control unit, that is hardwired control unit. So today we learn about microprogram control unit. We'll do for a few questions on that. Also we'll understand the difference between horizontal and vertical microprogramming, which is also a type of microprogrammed control unit, the differences, and we learned about RISC and CISC CPU design. Just a few theoretical points. Okay. So what is microprogrammed control unit? So microprogram, as the name suggests, it is programmed within the CU, within the CPU. Okay. Here what happens in our control unit itself, we have a memory known as control memory. We have a memory known as control memory. Control memory. Okay. And in that memory we have few things stored. What is it? Is it stored? It is stored we stored a lookup table. Lookup table. Now what does lookup table means? Sometimes in short form we call it LUT. LUT. What does it mean is that what does that instruction means that will be mapped to produce a control signal. Okay, what do I mean by it? Let's take an example. I have an instruction 10. This is the opcode. Okay, this is the instruction opcode. Now if this is 10, right, what it will do is there is a lookup table. There will be a lookup table. I haven't drawn it. There will be some lookup table in the control memory. Okay, and somewhere the decoding, like the control signals, like what signals does the control unit needs to send to all the elements will be present of this 10, right? Somewhere here some control signal 10, somewhere it will be present in LUT. Okay, so what we'll do, we'll just directly go here and then send this instruction in the control unit. So control unit understands, okay, I need to, for this 10 instruction, for let's say add instruction, the control word is 00 100 100, something like that. Okay, it will be present in the LUT. So it will directly take this from the lookup table. Previously we didn't have any lookup table. What we had hardware. In hardware control unit we had hardware logic. For each instruction we had a hardware logic, if you remember. So previously in hardwired control unit we implemented the same. We implemented the same using hardware. Okay, I am running out of space actually. Okay, what we can do is we can maybe take this more on the down. Same. Using hardware, but now it is present on memory. So obviously there is a drawback. We are using memory, we are using storage, so it will have some drawback. Also we need memory access here. We're accessing the memory, right? Hardware, it was instant. As soon as the instruction got, there was decoding logic ready, and in hardware it instantly decoded everything, right? It was all hardware present. Okay, all the signals were hardware present, but we have to do memory access, so that will take time. That will slow this microprogram control unit. Also we have to store it somewhere, right? So that will also cost us storage. So obviously hardware also we have to make the hardware, so that is a disadvantage. Also we can change this. We can always change this memory if we want. Okay, like not everyone can change this. It is restricted to the designer or some people. Not everyone can change it, but yes, it is changeable. It's not like it is done in the hardware and I cannot change it ever. Okay, so That is what is written here. A microprogrammed control unit uses micro instructions stored in control memory to generate control signals. So what does each micro instruction or each micro operation means? Okay, it will what is micro instruction? Actually, micro instruction is a collection of micro operations. That's it. So what does each micro instructions mean? So add, right? If I write add R1 plus R2, it is a micro instruction. Just hold on a second. It is a micro instruction, okay, where there will be many micro operations. First I will load the instruction from the instruction register, then I will load the values, then I will add the values. So there are many micro operations involved. So I have already explained this previously as well, that micro instruction is what? It is a collection of micro operation. Okay, so there are multiple micro operations. Now obviously the CPU only performs micro operations, right? So control signal will break it down from micro instruction to micro operation. That will be defined here in the LUT. We'll see that as well, how it does that. Okay, sorry, just hold on. So yeah, stored in my control memory to generate control signals required for executing instructions. It functions like a lookup table where each instruction has associated microprogram consisting of control words. So each micro instruction will have a control word, okay, in the LUT, and we'll take the control word from the LUT itself. So here I have given you a block diagram. So if I see, I have this instruction code that goes into some next address generator sequencer. We'll understand this as well, what is sequencer. Then it goes to control address register. So the control address register actually maps to the where the control signal for this particular instruction is present, where the control word is exactly present. So control address register, it maps the control word. Next we go to the control memory. Using the address, I know where that particular control word is present. I will go to the control memory. So here in control memory, all the control words will be present, which generates a control signal, right? Then from this control word gets copied to control data register, and then we have a decoding circuit to which signal to turn on and off. That decoding circuit we have, and finally our control signal gets generated. Okay, so this is the sequence or flow of a microprogrammed control word. So now we will understand this block. What is next address generator, also known as control word sequencer? So control word sequencing is a key aspect of microprogrammed control unit, determining the sequence of the micro instruction control words that are fetched and executed to carry out an operation. So I told you, right, it contains micro instructions. Okay, so in micro instructions, like control word is what? Each micro operation. Control word is what? Each micro operation. So a micro instruction will have a collection of micro operations. So this is a instruction, micro instruction I1. Let's say I1 is add R1 R2. Okay, so it will contain many micro operations. So we have many micro operations here, right? But obviously the control unit has to know, is this the start of the micro instruction and is this the end of the micro instruction? So where is the start of the micro instruction and where is the end of the micro instruction? That the control unit must know. Who tells the control unit? Control word sequencing. So here if I see, here I have a next address generator, right? It understands whether my whole micro instruction has finished, because all these individually are micro operations. So it will understand that where is my next micro instruction. Okay, so this I1 instruction, we start from here. Okay, then it is just like PC. Where is my next micro instruction in this sequential here, right? Sometimes what will happen is you will have branching, you will have looping. Okay, if you have branching, that means you will branch to some other micro instruction. So that branching is also taken care by control word sequencing. Okay, I hope you know what is branching, what is looping, all these things you know. Okay, so branching means I'm going to some other micro instruction. I will not complete this micro instruction. I will go to some other micro instruction. Okay, so the sequencing process defines the flow of control through the microprogram and ensures that the control unit correctly generates the signal required to execute the instruction. So the instruction can have branching, it can have looping, anything. Sequencer is a hardware component that generates the address of the next micro instruction based on the current control state. This should be not micro instruction, this should be actually micro operation. The words are very important. If somehow we mess up micro instruction operation, the meanings will change. The sequencer determines, by following a predetermined sequence by branching based on the conditions. So there will be some predefined sequence. All this will be defined in the LUT. All this will be defined, right? That's why we have a separate hardware unit to understand, okay, whether we need to branch or we don't need to branch, all these things. Now, what is, like, let me give you an analogy of control word sequencing. What is control word sequencing? Imagine a recipe book where each recipe control word tells you exactly what to do with the signal. So those are micro operations, right? You have to make chicken kofta. So first you have to buy the chicken, obviously, get this much 500 grams of chicken, then some amount of soya sauce or some amount of vinegar. I don't know, okay, what recipe you need, but I'm just giving you an example, okay? Ingredients you will need. So you got all those things, then you have to like boil the chicken for 30-10 minutes, okay? It all depends. Now the sequence actually is given in the recipe book. All of it is written in the recipe book. So recipe book is our LUT. Recipe book is our LUT from where you take all the information. But the sequencer is like a chef deciding whether to move to the next step or jump to a specific part. Now you have, like, you are very rich and you have a personal chef with you, and the chef tells you whether you need to follow this particular, like put soya sauce or not, because chef has so many years of experience. He might have his own recipe, right? So he knows exactly, if I put soya sauce here, will it be best or not? Because obviously recipe book is available to everyone, but can everyone make that good amount, like good food, right? Good tasting food? No, right? Everyone cannot make that. We have special people like our moms and obviously other people. So obviously you need someone. So chef is that person who tells you whether you need to do, like, what sequence you need to follow. Chef will tell you sequence, whether you need to put the soya sauce or you don't need to put the soya sauce, okay? It tells deciding whether to move to the next step or jump to a specific part of the recipe based on the dish being prepared. He has experience. He can have his own. He has made his own dish, right? So it depends on his own taste. Just like sequencer calls. So it depends whether in the instruction have a branching, or the user wants a branching, or user doesn't want branching. User wants loop. Looping means multiple times repeating is the same instructions. It depends on the user. Okay, this time I hope you understood this point. So there can be like many types of sequencing. One is sequential sequencing. This means the next micro instruction is fetched from the next address in the memory. Okay, not micro instructions, micro operation. This will be micro operation. I think this also. And this also will be micro operation. Yeah, now it is fine. Don't get confused sometimes with micro operation and micro instruction, okay? The smallest possible thing, that is micro operation, and the collection of those micro operations is just a micro instruction. Sometimes they are used interchangeably, okay? So don't get scared by that terminology. The next micro operation is fetched from the next address. It is sequential, okay? Simplest form of sequencing. Conditional branching. In some cases, the sequencer branches to different micro instruction. So it is true, it will branch to different micro instruction. Why? Because if I am, let's say, in I1, okay, and there is some condition that check if the result is 0 or not. If it is 0, branch to instruction I3, okay? So it will go and branch to instruction I3. So that is the conditional branching. Then looping. For certain instructions or operations, a loop may be employed where the sequencer repeatedly fetches the same set of micro operation until so this will actually might be micro instruction only. The same set of micro until condition is met. Okay, so what we do is same set of micro operation. This is correct. Same set of micro operation. So we check if I, like, what is this? This is, we are branching, right? If result, right, accumulator value is not equals to 0, then branch to I4 instruction in the control memory. Now here if I will do like I less than 100, and then I will increment I plus plus, and I will say if this condition is true, right, I have started from location I1, so I will again go to branch, go to I1 again. If this condition is true, if this condition is met, I will again go to I1. Okay, so it will keep on repeating itself 100 times if I is starting from 0. Just simple loop. Okay, so those are few control word sequencing. Okay, and your control memory will contain what? Your control memory will contain two things. One is the control word. Okay, another one is the next address of the instruction. So remember, this is the memory present in the hardware, in the control unit. I have already told you this will be present. Control memory will be present. Memory present in control unit itself. Okay, that's why the access is faster, but still it will take some time for us to access a memory, right? It contains the control word and the next address of the instruction. So these two things are present. Okay, so it's, and remember, everyone cannot access it. I have already mentioned everyone cannot access it. CPU or CPU cannot access it always. So here CPU can't access. Okay, it is not like ROM or RAM. Okay, not ROM or RAM. CPU doesn't have access to it. Control word is the leader of everything. So you don't have access to your manager's details, right? Obviously you don't. So that is the thing. So yeah, I hope you understood each control address in a control word, in a control memory, contains the control word obviously and the next address instruction. What is control word? You already know that. Okay, so let's do a few questions. From there our concepts will be more and more clear. So this is the first question. Consider a CPU with the following characteristics. We have 100 control signal bits. Okay, so I have 100 control signal bits. Okay, so then each instruction requires 50 micro operation, and CPU supports 12 distinct instructions. So each instruction supports 50 micro operation, and we have 12 distinct instructions. So how many micro operations I have? So this is mu, right? Don't get confused by m and mu. This is mu. How many micro operations I will have? 12 into 50. This many amount of micro operations I will have. So how many bits will I need to define this many amount of micro operations? This is 600, right? So how many I will require? I will require log upper bound log of 600, that is 10 bits. Then a 4:1 mux is used for instruction decoding. So we have a 4:1 mux, right? And if I have a 4:1 mux, how many bits will I have? I will have 4 bits. Now why do I need a 4:1 mux? Okay, for mux select lines, it will have a 4:1 mux. So 4 bits. Why will I have 4 bits? Why will I require mux here, right? If you see, I have to convert, like here I have a decoding circuit. I have to convert the bits into signals. Okay, bits into signals. If you remember, every PC has its in and out. The instruction register has its in and out. Each of it has its signal, right? So which signal to turn on and turn off, mux will do that. Control word sends that. Okay, but mux actually finally converts it. So we will require a mux. Okay, so here decoding circuit, mux and all those things will be present. In hardware, mux is anyways present. In microprogrammed also mux will be present, just to send those signals, right? Mux to connect everything. So how many bits, select line bits I will require, because it is a 4:1 mux, right? And if you have studied digital electronics, you will know I will need 2 select lines. So here I was wrong actually. Okay, I messed up here. I hope you have studied digital electronics. If I have a mux, right? If I have a 4:1 mux, this is a 4:1 mux, correct? What does 4:1 mux does? It takes 4 inputs here, okay, and gives 1 output. And to select any of these lines, right, I will require a logic. I will require 2 select lines, S1, S0. Okay, what happens is the control word comes here. Okay, now it distributes the signal, right? So first bit will be for the first signal, the second bit will be for the second signal, and so on. So obviously I need a mux. Okay, so that is the decoding logic basically. So this S0, S1 will be the select lines. These bits will be required in the control word, because this also will be provided by the control signal only, which lines to select, okay, which signals to turn on basically. Okay, that will be decided by the control logic. So that should be also present in the control word. Okay, so for mux select I will require 2 bits. How am I calculating 2 bits? It is a 4:1 mux, so it will be 2 raised to power 2, right? 2 raised to power 2, that is I will require 2 bits to define this. If it was a 16:1 mux, what was the formula if you remember? It is 2 raised to power 4, so I will require 4 bits to define the select line. If it was 8, I will require 3 bits. So simple as, right? So here I will require 2 bits mux select. So what are they asking? First, the question is the total number of micro operations in the control memory. We have already calculated that. Like while reading the question, the total number of micro operations will be 600, because I have 12 micro instructions, and I have told you I have like those instructions are combination of are collection of micro operations. So each micro instruction has 50 micro operations. So total 15 to 12, 600 micro operations. So total how many micro operations? I will have 600 micro operations. Okay. Now, the number of address lines required to access the control memory. How many address lines I will require to access the control memory? Now, the control memory has 600 different instructions. So how many bits I will need to store those instructions? 600 different, right? So I will I will store my instructions like this, right? If I just bring, this is my control memory, correct? This is my control memory. So I'll store my instructions like this. How many address lines I will be requiring? Basically, there are how many? 600 instructions. So 600 micro operations. So I will have 600 of this, right? Present 600 control words. So 600 micro operations, meaning I will have 600 control words. So I will need to store 600 control words. So 600 different address I will have. So total how many bits I will require? Simply the log of this. I have already done that. Okay, solve that. So it will be log of 600, right? So that will be 10 bits. I will be requiring 10 bits or 10 address lines. 10 bits or 10 address lines. 10 address lines. Okay. So it will be 10 address lines. Just hold on a second. I will check if everything is recording or not. Yes, everything is recording fine. Yes, I will be recording 10 address lines. Now let's move on to the part C. What does the part C tell us? The control memory size in bits. What will be the control memory size? This is very interesting, right? You know how to calculate the control memory size. There are address, and what does each address contain? That's how we define the control memory, if you remember, right? If you remember correctly. So how many bits does the control memory contain? So that we have to write down, right? So I have total how many of this control word? I have total I will require 10 bits, and in this 10 bits each control word contains how many? Each control word contains how many bits? So I already know that I have 100 control signal bits. So each control word, what will be each control word containing? So I have here a control word, but the first portion of it is gone. 100 bits is gone for control signal. Okay, this is gone for control signal. Now next portion is for what? Next portion is for the mux select lines, right? Mux select lines. And don't forget, I have explained the control word sequencing as well. So this control word will contain the information about the next address as well. Next address, next instruction address. So for mux select lines, how many bits do I need to provide? 2 bits. For next address, how many bits do I need to provide? It is address, and address has how many bits? 10 bits. So each control word, this is a control word. Each control word contains how many bits? Each control word contains total of 100 plus 2 plus 10, that is 112 bits. Each control word contains 112 bits. So total, how much memory I will have? I have, like, each control word here is 112 bits, and how many of this I have? 2 raised to power 10, because it's a 10 bit address line. So 2 raised to power 10, it is 2 raised to power 10 into each control word bits, right? So this is in bits. So this is what? This is almost equals to k. In computer, this is defined as k. So this will be equals to 112 k small b. 112 k small b. Now if I want to write it in terms of bytes, how will I write it in terms of byte? Small b, this means what? This means kilobytes, not bytes, kilobits. Kilobits. And what about if I want to write it in bytes? I have to divide by 8. It will be 14 kb. Okay, this is capital B. So this is kilobytes. Okay, so just be careful. And one more thing I want you to warn is, don't make this silly mistake that I have only 600 micro operations, so I will have only 600 of these control words, and what I will do is I'll simply multiply the memory. Memory will be CU memory. You will do 600 times each, like, what does each control word, how many bits does each control word contains? Total 112 bits. 112 bits. This will be totally wrong. Why this will be wrong is, you have told that you are providing 10 address bits, right? 10 address lines. And I know that there is a wastage of space. That few control words will be wasted. Why few control words will be wasted? Because I'm not using all of them, right? I out of 1024, I'm only using out of 1024, I will be using only 600, right, for my operation. And it's okay. I cannot use 9 bits. If I use 9 address lines, it will be 512. So you will be left with 88 control words, like you will not be able to decode, right? So obviously you will require more, you will take extra, and your I'll be only using 600. So the 424, right, 424 words here, 424 words, 424 bytes, or like words, they will be just left empty, will be empty, and it's okay. But you have already assigned 10 bits for address lines. You cannot do like half 600 you will store for control unit memory and you store some other things in there. You cannot do that. You cannot do that. Once you assign 10 bits, so all the 10 bits, all whatever memory is there, all of it will be used for control unit. It's okay if you are not using all the instructions, that's fine. You're not using all the memory, that's fine, that's your decision. But you cannot do it like this, that you are only using 600 and you are keeping empty 424 for something else. No, it doesn't work like that. Okay, it is a separate quantity. It is within this control unit. You cannot use it for some other things. Okay, so don't multiply 600 by 112, you will make a mistake here. So that's what I wanted to mention. Now there are two things for your for your control memory. Okay, there are two types of control memory. One is, just hold on, I will check if everything is here is correct. Yeah, everything here is correct only. I'll just quickly check the calculation. Actually 600 into this, yeah, everything is correct, everything is correct. So what I was talking is that there are two types of control memory. One is horizontal microprogramming, another one is vertical microprogramming. So what does this horizontal and vertical means? We'll understand this with questions also. In horizontal microprogramming, one bit is assigned to each control signal. So just what we learned, right? This is horizontal. Everything is in horizontal, right? So each control signal will be assigned one control bit. Okay, just like PC in, PC out, they will be assigned one control bit only. All control signals are explicitly specified in the control words. Okay, all control signal will be specified in the control words. Here, faster as no decoder is required. Mux will be required. Okay, mux will be required. Which signal to pass through, which signal to make high, that will be required. But no decoder. Mainly decoder will not be required. Large control memory size due to longer words. So the words are very long, right? It's like 112 bits long. It is a very long word. Okay, so it will take up more space. So if I want to reduce the space in the control memory, we can use a concept known as vertical microprogramming. Okay, so this happens when control signals are grouped and encoded using fewer bits. A decoder generates the actual signal. Okay, how do we do it? I will explain. Just understand this. We will use horizontal microprogramming when we prioritize speed, and we will use vertical microprogramming when we prioritize I think this will be what do you say, memory. We don't have much storage. Advantage is we will use smaller control memory due to compact control words, because control words will be like smaller, because we will decode all the control signals with a decoding logic. So obviously it will be slower because there is a decoder. So obviously we will need a decoding logic. But do remember one important point: to use the decoding logic, right? To use the decoding logic, all signals in same group must be mutually exclusive. All the signals in the same group must be mutually exclusive. Okay, what do I mean by it? So in horizontal, we already know, like we provide control signal for each of the bits, right? Each of the control signals. So we provide bits for each of the control signals. In vertical microprogramming, what I will do is I will have, let's say, this CS1, CS2, just hold on, CS1, CS2, then I will have here CS3, CS4. So if I would have used horizontal microprogramming, how many control signal bits I will require? I will require a total of 4 control signal bits. 1, 2, 3 and 4 control signal. 1, CS1, CS2, CS3 and CS4. Okay, so total 4 bits. With what? With horizontal microprogramming. Horizontal microprogramming. Okay, now if I want to use vertical microprogramming, how will I store the bits? So what I will do, I know one thing, that if control signal 1 is on, right, control signal 2 will never be on. They are mutually exclusive. If control signal 3 is on, control signal 4 will never be on. So what I can do, I can put them in groups. I will write here that my CS1 and CS2 and CS3 and CS4, they are mutually exclusive. They are mutually exclusive. Like if that, what does this mean? This means if one turns on, other will never be on. Example, PC in and PC out. Can they simultaneously be on? Okay, there can be few cases where they can be simultaneously be on, but I am taking an example. Generally, PC in, like when it is taking the input and when it is giving the output, they won't simultaneously be turned on, right? That is a general convention. So I can give you like many examples like this. So if they are not simultaneously on, what I can do, I can put them in groups. What I will do, I'll put them in groups. So this will be my control word now, and the control word will have group G1, G2. Okay, we'll have group G1, G2. So what I can do is simple put a 1:2 decoder, correct? 1:2 decoder. So this group contains like control signal 1 and 2, but has only 2 bits. 3 and control signal 4, but it has actually only 2 bits, right? So if G1 bit is on, I'm just giving you an example, don't take it as it is. So if this G1 is 0, then this decoder will select what? This decoder will select basically, like there is some logic, it will select 0, 1 or something like that. And if this G1 is 1, then this decoder will select 1, 0. It will turn on other signal. So I have implemented that logic. First it will select the CS1 if it is 0, it will select the CS2 if it is 1. So I have got a decoder. Okay, so how many bits did I require? I require only 2 bits and 2 decoders as well. So obviously this will cause some delay, but it's my advantage, right? I reduce my size has been reduced to from 4 bits, it has been reduced to 2 bits. Okay, but what is the disadvantages? The disadvantages is 0 decoder to 2 decoder. So memory less but slower, and I need to implement hardware logic, right? So that is also a disadvantage of this particular thing. So I hope you understood what is the difference between horizontal and vertical microprogramming. So let's do a few questions on this. Arrange the following configuration CPU in decreasing order of operating speeds. I know we have studied 3 types of control unit, right? One is hardwired control unit, another one is horizontal microprogramming, another one is vertical microprogramming. Now, in hardwired, everything is hardwired, so it will be very, very fast. We don't have to go to the lookup table and have a memory access, right? We don't need to do that. So hardware will always be faster. So which they are telling me in decreasing order of operating speed. So highest operating speed will be of hardwired. So in the first element, it should be hardwired. I can see these 2 options are hardwired. Now I move on to the next element. Horizontal microprogramming or vertical microprogramming. In horizontal microprogramming, the control signals are directly in the control word. So even though it is slower than hardwired, yes, but it is faster than vertical microprogramming. Just reason I have explained here. We don't need a decoder. It will take some time, right, to decode that. So horizontal microprogramming will be faster than vertical microprogramming, but will take more memory. But we are not talking about memory here. We are just talking about speed. So horizontal microprogramming will have more speed than vertical. So option B will be correct. So through this question, I just wanted to clear the concept. In horizontal microprogramming, does not require use of signal decoders? Yes, it is correct. It does not require use of signal decoders. Results in larger size micro instructions than vertical microprogramming. Yes, we require large size micro instructions because like each bit, like all the control signals are present in each bit, right? So we have huge number of bits in the micro instructions of the control word. So next is uses one bit for each control signal. Yes, that is what I told, right? Yes, it uses. So obviously all of them. So don't always in the examination hall be in a hurry that you read the first option, it is correct, and tick and you went ahead. Read all the options. Okay, let's do this question. So this question is also interesting one. We have like from this question we'll understand a very interesting concept. I will explain that. A instruction set of a processor has 125 signals. So instruction set has 125 control signals, which can be divided into 5 groups of mutually exclusive. So if one is on, the other will always be off. Okay, signals. Group 1 has 20 signals. So G1 has 20 signals, G2 has 70, G3 has 2 signals, G4 has 10 signals, and G5 has 23 signals. Okay, how many bits of control word can be saved by using vertical microprogramming over horizontal microprogramming? So how many bits I will require to explain 20 control signals, right? So this is a decoder. So in a decoder logic, basically how many bits I will require? So this, the right hand side is 20, right? It should give me 20 bits for the control signal. So left hand side, how many bits I will require? It will be depending on the, right? It will be like if you have studied digital electronics, it will be log of base 2 20, correct? Not this, upper bound of 20. So upper bound of 20 is simply equals to 5 bits, right? So here I will have 5 signals. Okay, this will be 5:20 decoder that will decode from 5 signals to 20, correct? So I will have 5 bits here for the group 1 G1. So I will just draw the control word here in vertical microprogram, but horizontal all the control signals will be present, right? So in vertical, okay. So here what it will be is basically what I will do is I have the control word G1 I have, then G2 I have, then G3 I have, then G4 I have, then G5 I have. Okay, so this, for this I will require 5 bits. Similarly for this, how many bits I will require? For this, how many bits I will require? 70. So what will be log base 2 of 70, upper bound is 7 bits, right? This will be requiring 7 bits. Okay, and what will be the log base of okay, this is correct, yeah, 7. What will be the log base of this 2? This will be only a single bit. This will be only a single bit. So this will be a single bit. This is for this group. So this is becoming a messy. And for here it is log base 2 of 2. It will be a single bit, right? That has already been proven. So side by side I will write the bits actually. That will be helpful for us. That will be helpful. So this will be equals to 5 bits, 5. This will be equals to 7. This will be equals to 1. And G4 I can directly do now. I can directly do, what is log base? What is log base? 10. So log base 10 will simply be 4, right? I will require 4 bits. And what is log base 23? Again I will be requiring 5 bits. I will be requiring 5 bits. Okay, so total how many bits I needed? So here 5 plus 7 12, 12 plus 9 21 and 22. So total bits in microprogram, vertical microprogram is 22 bits. This is whole a control word, right? But if I would have used horizontal microprogramming, how many total bits I would have required? Ignoring like 22 bits is for vertical only for the control signals, right? Only for the control signals. There will be next address, all those things will be there. I am ignoring that because that will be same for everything. That will be same, right? That will be same for the vertical microprogram and horizontal microprogram, correct? In horizontal microprogram, for control signals specifically, I would have had to given all the bits for the control signal. How many total control signal bits? 20 plus 70 plus 2. 20 plus 70 plus 2 plus 10 plus 23. So this will be 20 plus 70, that is 120. 120 plus 2, 122. 122 plus 10, 132. 132 plus, okay, just hold on. 20 plus, sorry, this is 90. This is 90, 92, 102, then 125. So total I have 125 bits. So how many bits did I save? So yes, these are for control signals. It will have the next address bits. It will have the mux. That is there, right? That is there. But that is same for both. That we don't save. We save only on the control signals. So bits saved, how much? 125 minus 22. So total of 103 bits were actually saved. I hope you are observing the difference, right? How many bits we are saving? Obviously, there is some time loss here. There is some decoding logic, more decoding logic gets into here, but we are saving this many amount of bits, 103 bits. This will be your answer for this particular question. So I hope you understood decoder concept. If you don't know, please go and study digital electronics. So we have to find out the width of the control memory of a horizontal microprogram control unit given for the following specification. So we have 16 control lines for processor consisting of ALU and 7 register. So we have 16 control lines for this particular ALU and registers. So we have 16 control signals, correct? And this we have to calculate for horizontal microprogrammed. Okay, so 16 control signal for horizontal microprogram, and we have a conditional branching facility by checking 4 status bits. So I will have 4 status bits. I will have to provide 4 status bits according to which the control unit will branch. So this is 4 bits here and here, 16 control signal bits. I'm using horizontal, so I have to provide all the bits. I cannot use decoding logic. Provision to hold 128 words in the control memory. What do I mean by 128 words? So control memory has, like, each row has control words, right? So how many rows I have? I have total 128 rows. So I have only 128 of these rows. So how many bits I will have for the address? How many bits? It will be log of 2 128. So this will be 2 raised to power how much? 7, right? I will have 7 bits or 7 address lines. Okay, so total for horizontal microprogramming, microprogram control unit, how many bits I will require? So total bits, right? They are asking me what is the width of the control memory? Width of the control memory, or each control word, what is the width of the control word? Each control word, that is 16 plus 4 status bits plus 7 address. So like your control memory will be consisting of this, right? Control memory will be here. I will have 16 control signals, then I will have 4 status bit, then I will have what? Then I will have 7-bit address. Okay, so this will be total 27. So 27 bits will be the width of the control memory. Now if they would have asked what is the size of the control memory, okay, what is the size of control memory? Size of control memory, what you would have written? You would have simply done 2 raised to power 7 into 27. So this would have been the size of the control memory. If you want to convert it into kilobytes, no, not kilobits, if you want to convert it into kilobits, what you'll do, you'll do 2 raised to the power 10 into 27 by 8. So it will be like whatever is 27 by 8, I will calculate it. It will be 27 by 8. So 3.375 kilobits. Okay, answer is this. Answer of the question is this. Okay, this is the answer, 27 bits. If they would have asked what is the size of the control memory, then you would have written it like this. Okay, 3.375 kilobits. Okay, I'm just solving the extra portion of this particular question. Now let's solve the next question. So we have this question: consider a CPU but all the instructions require 7 clock cycles to complete execution. So all instructions will require 7 clock cycle. Any instruction will require 7 clock cycle. Okay, there are 140 instructions in the instruction set. So I have 140 instructions. So how many bits I will require for this instruction? I will see 140 instructions. So how many instructions I will require? Total number of instructions will be log upper bound of 140. How many bits I will require to define this many instructions is 8. Correct? I will require 8 bits. And I have 125 control signals. 125 control signals are needed to be generated by the control unit. So this will be generated by the control unit while designing horizontal microprogram control unit. Single address field format is used for branch logic. So a single address field will be used for branch logic. So like they have told me, like we are using a horizontal microprogram, right? So if I am using a horizontal microprogram, how will my control word be? First I will have control signals, then I will have next address field. Okay, and I will see if they are telling me about mux and all. If they are not telling me mux, I will not write the mux bits. Okay, if they are telling me, I will write the mux bits. And I have how many different instructions I have? Total 140, right? I will require 8 bits for 140. So what you will answer is, no, this is not 8 bits. Sorry, this is incorrect. This is 8 bits. Yeah, 8 and 9. Yeah, this is 8 bits only. Yeah, 9 will be 512. Yeah. So what you will answer? You will answer here 8 bits. Okay. And what they are asking? They are asking that what is the minimum size of the control word and control address register. So 8 plus 125. 5 is 133. You are not seeing that in options. And control address register also is not present. Okay. Control address register should also be 8 bits, right? Its address field should have been 8 bits. So it is not present. So what went wrong here? What went wrong? I made a silly mistake. They gave me this information, right? 7 clock cycles. And this is instruction. This is not micro operation. Control word stores the micro operation. So this is wrong. This thing is wrong. This thing is wrong. So I will write here. I write down the important point that control word stores micro operation. Okay, control word stores micro operation. It does not store like instructions. It only does micro operation, right? So how many, like all instructions have 7 clock cycles. So 1 clock cycle is 1 micro operation. Remember, 1 clock cycle is 1 micro operation. So total number of micro operations, total number of micro operation. How many total number of micro operation I have? Total number of micro operation is 7 times 125. 7 times 125. So not 125, sorry, not 125. I have total how many? 140 instructions. So 140 instructions has 7 cycles each. So how many cycles or how many micro operations I have? 7 times 140. So it will be 980. So this many number of micro operations I will have. So for this, how many bits I will need? Total number of bits. Because I have to store this micro operations, right? Each micro operation will be stored in each control word. Each control word corresponds to each micro operation. Total number of bits for micro operations. Okay, so this will be the address line bits because I have to store those control word, right? It will be log, upper bound of log base 10 980. So this will be equals to 10 bits. So actually I will require 10 bits to store all those data, right? This is the address line bits. So like what am I talking about? So I have control memory here, right? I have control memory here, and this many micro instructions I have. This is I1, I2, something like that, right? Micro operations I have. So total how many I have? Total I have 980. So how many bits I need to define for each of these address fields? Only 10 bits, right? 10 bits will be what? It will be 2 raised to power 10. It will start from 0 to 2 raised to power 10 minus 1, that is 1023. 1023 should be enough. So total 1024 I will have values, out of which only 980 I am using. Unused are there. I don't care. I will leave it empty. I don't care about that. Okay. So actually my control word will consist of control signals, which will be of 125 bits, and it will consist of address, next address instruction. So it will be 125 bits and 10 bits. Okay. So what are they asking? They are asking me the minimum size of the control word. Minimum size of the control word, you have to minimum at least provide 125 bits, 135 bits. You can provide more. Here in the address field, right, you can provide 11 bits. It will be able to store more instructions. Okay, I am not using it, that is my decision, but you are providing 11 bits. But minimum is you have to provide minimum 10. If you provide 9, I can only describe 512 instructions. 512 instructions. I cannot describe the other remaining out of 980. I cannot describe the other ones. Okay, so I have to at least provide 10 bits. So that's why minimum size of the control word will be 135, and the size of the control address register, you have to at least provide 10 bits. Same reason. So option D will be correct. Okay, just be careful about the information, and like this happens with me also. Sometimes the questions of the COA are very big. You miss out on some information. You miss out on some important information. Just be careful regarding that. Okay, so let's read the next question. Okay, so this question is also very good. This question is also very good. We need to be very careful in this question. Okay, so I will solve this question. So here a microprogram control unit is required to generate a total of 25 control signals. So I have total of 25 control signals. Assume that during any micro instructions, at most 2 control signals are active. During any operation, right? During any micro operation, at most 2 control signals can be active. So it can be CS1, CS2. Okay, it can be CS2, CS3, it can be anything. So how many combinations I have? I have 25 C2 combinations. Out of 25, any 2 will be always active. I can choose any 2. Okay, this many number of combinations I have, right? Now what are they asking? Assume that during any, okay, this is minimum number of bits required in the control word to generate the required control signals. Minimum number of bits. Whenever they are talking about minimum number of bits, then to generate a control sequence or control word, which one I will choose? I will obviously choose the vertical microprogram. Whenever they are asking me minimum, first start of my thought process will be, we will choose like what type of architecture we'll choose. We'll choose vertical microprogrammed. Okay, so next is what required in the condition to generate control signal. So how many minimum will require? So let's start off, right? I can group them up. Okay, so in horizontal, what we would have done in horizontal, simply I would have done here 25 bits, right? All 25 bits would have been separate control signals. So 25 bits would have been there in horizontal. But obviously we will not use horizontal because I am saving on space. Okay. Now what if I choose vertical? Now in vertical, like I know thinking this for the first time will be difficult. I also wasn't able to figure it out for the first time. So in vertical, your first thought process will be just add them as groups. Okay, G1, G2, and like total we have 25 signals, so I can add total of 13 groups. and if I will assume that if one is on, other one will be off. Okay, but the problem with this approach will be that I don't know like which are mutually exclusive, because they have told me that at most two control signals will be on, but which control signals together? They have not mentioned me the combination. Okay, so this approach of two control signals each is wrong. Okay, because I don't know, because I don't have the information about the grouping of the control signals, right? I don't have that information. So I don't have that information. Now if I don't have that information, so what thought process I can do? So first thing what I can do is I need to choose minimum, right? I cannot choose a single group. What I can do is I can choose two groups. Okay, in vertical, if I choose two groups, if I choose two groups, G1 and G2, and if you tell me that in group G1 you tell me you are choosing 13 control signals, and in group G2 you are choosing 12 control signals, but they are telling me at most two control signals will be on. At most two control signals will be on. Now if two control signals are on, then what will happen is, if I here, let's say in this G2 group, right, I have CS1 and CS2. Now they can be on together as well. The first rule for a vertical microprogrammed group is the signals should be mutually exclusive. If this is on, then this should not be on. But do I know? I don't know. They have not given me that information. They have told me that at most two signals will be active. So CS1 and CS2 can be active together, because I don't know if they can be together active or not active. So this option, this idea is also gone. But one thing I can do is I can have this decoding logic, right? I can have this decoding logic, so I'll keep it. What kind of decoding logic? That if I choose here 25 control signals and here are also 25 control signals, so I will develop a logic such that only at most two can be on, right? So only one of the control signals here will be turned on, okay, and the other control signal here will be turned on. So the logic will be developed like that. So one more thing can happen. They have told me at most two control signals are active. It can happen that none of the control signals are active. So I have to choose another state for that none of the control signals are active. Okay, +1 where 0 control signals are active. Here also +1 where no control signals are active. 0 control signals are active. So that can also be a state, right? No control signals are active. Okay, so that state also I have provided. Now what kind of decoder I will require? So again I will do the same logic, that is log of 225. That is equals to what? That is equals to 5 bits. So total how many bits I will require? 10 bits plus 10 bits, that is 5 plus 5, that is 10 bits. So minimum number of bits that you will require, okay, control word length or control word width, okay, it will be 10 bits. Option C. This is a GATE question actually. This is a very, very old GATE question, and I do agree the wording and all these things coming out of the brain at that examination hall is difficult. That's why I would have not come into my brain. Okay, I would have also skipped this question, because this is a very, very difficult question, and understanding this kind of thing, right, takes patience and takes a lot of time. So I also would have skipped this question. I wouldn't have solved this question. So don't worry if you were not able to decode the logic. I also was not able to decode the logic. Okay, so it's fine. It's totally fine. Just understand how to do this type of question. Next time when it comes, you have this in your mind. Okay, I can solve the question like this. This part is also very, very important. That what happens if none of the control signals are on. Okay, so that particular state also you have to choose. So let's read another question. The micro instruction is to be designed specifically none or one of the 3 micro operations of one kind, none or up to 6 micro operations of another kind. Okay, so none or one of the 3 micro operations of one kind will be active. Basically they're mentioning. So this can be defined as a group G1, where I will have 4 states, right? 4 control signals where either none of them are active or one of the 3 are active. So I have CS1, CS2, CS3. Either none of them are active. If none of them are active, I have to choose another special control signal, that is will be control signal 0, that specifies that none of them are active. Okay, or one of the 3 are active. So either one of the 3 are active, right? Any one. So all these 4 situations cannot happen once, right? All these are separate entities. Either none of them will be active or one of the 3 will be active. So this can be grouped together. Okay, this whole thing can be grouped together. Why am I talking about groups? Because in the question they are telling me the minimum number of bits. Whenever they are talking about the minimum number of bits, then I have to think about vertical programming and grouping. Now they tell me none or up to 6 micro operations of another kind. None or up to 6 micro operations of another kind. None or up to 6 micro operations of another kind. So I have the control signals CS4, CS5, CX6, CS7, CS8 and CS9. So I have 6 different control signals and all 6 of them can happen, up to 6. They have told me up to 6. Any 6 of them can happen. Can I group them? No, I cannot group them. Okay, and again they are telling me none. For none, right? For none, I have already taken a state here, right? I have already assumed a state for none here. Okay, I will also draw the control word. There also you will understand this better. This is my control word. Okay, this is my control word. Where I have group G1, which has all the 3 control signals: control signal 1, control signal 2 and control signal 3. Also I have another state known as none. Okay, if none of the 4 control signals are on. Now I cannot group them. These signals I cannot group, right? This I cannot group because it is not possible. So because any one of them can be on anytime. Okay, so it will be G3, G4, G5, G6. Okay, 1, 2, 3, 4, 5, G7. Now we will say you have to add another group G8 that also supports this none action, right? None of them should be on. Actually, that none has been taken care here, right? I have already chosen the none here. If none of the control signals will be on, that has been already taken care in this group 1. Because if all of these are off, so that means only none is the possible state, right? So none will be on in this group G1. So it has already been taken care of. So I will not take care it again. So total how many bits I will require in this particular group? As I require minimum number of bits, that's why I am using vertical microprogramming. Okay, so it will be log of the number of states. How many number of states I have? 4. So it will be 2. Okay, so here how many bits I will have? 1, 2, 3, 6 bits. So minimum length of the control word. Okay, minimum number of bits. Control word length, or sometimes they call it width. Minimum is 8 bits. Okay, this will be the minimum width of a control word, 8 bits or a byte. So this is also an interesting question. I hope you understood the concept of this particular question from the previous question. The previous question is difficult. You can leave it if you are not able to grasp the concept totally. Let's solve another question. So we have this question where the micro instructions stored in the control memory of a processor have width 26 bits. So each control width, right? Each control each control signal or a control word width is 26 bits. Each micro instruction is divided into 3 fields. Micro operation of 30 bits. So each micro instruction is divided into 3 bits, micro instruction, or sometimes they call it micro operation as well. So here I have the opcode, basically opcode. This is 13 bits. In next address field X and a mux select field Y. So this is a next address field X and Y. So this is address and mux select lines. There are 8 status bits in the input of the mux. So in the input of the mux there are 8 status bits. How many select lines I will require? So they have told me mux input is 8 status bits or 8 bits, and output of mux I know it is it's always a multiplexer, so it will be one line. So how many select lines I will require, or how many bits I will require to control the mux? It is log base 2 of 8 upper bound, so it will be 3 bits. So I will require 3 mux select lines. Okay, that will be S0, S1 and S2. How many bits are there in the X and Y field? So in the Y field I have got the value, that is 3. This is my Y. And what is the size of the control memory in number of words? So I have to read this, like visualize this diagram. So I am seeing this is a bus, right? All this is a bus. So this mux has 8 inputs, and these are the select lines and only one output. Okay, so it has total, so this X, right? This X is the going into the control address register, so this X is the input to the control address register. Okay, so I have 8 select lines here. And how many bits I have here? How many bits I have here? 3. I have 3 bits here, right? I have 3 bits here. Here I have 3 bits because this is the select line. This is the input to the mux. This is 3 bits, right? And this is 13 bits. Each micro operation opcode length is 13 bits. And they have told me that the control word width is 26 bits. So this overall thing, right? This whole thing is 26 bits, out of which 13 bits is opcode and 3 bits is mux select. So obviously I know the length of this whole thing is 26 bits, out of which I know this is 3 bits. So what will be the remaining one? It's very simple, right? It will be only 10 bits. So address line, number of address lines or bits, address lines or bits will be simply equals to 26 total width of the control memory minus the Y mux select lines. That will give me the X, right? This is the Y. Okay, sorry, I have the opcode length as well, right? I have the opcode length as well minus the opcode length. So this will give me 10 bits. This is actually 13. Give me 10 bits. So what are they asking? They are asking me, first of all, what is X and Y fields? X is 10 bits. X is 10 bits. So 10 bits is here. So these two are the possible options. Next, Y is 3 bits. Y, both of them as 3. Now what is the next thing? The size of the control memory. How to write the size of the control memory? What will be the size of the control memory? Size of the control memory, size of control memory. We know how to calculate the size of control memory, right? How to calculate the size of the control memory? The size of the control memory will be the total number of addresses, total number of control words. How many I have? 2 raised to power the address field bits, that is 2 raised to power 10 into how much? Okay, what have that in words, right? Total in words. So you have to take care in words. So like how is my distributed? This is in, and what is the size width of each control word? It is 26 bits. But actually what are they asking? They are asking me what is the total size of the control memory in words. So control memory has this control word 1, control word 2, like this. How many it has? It has from 0 it has to 2 raised to power 10 minus 1, because this many address bits I have, right? Total how many it has? Total it has 2 raised to power 10. So this is in bits, but they are only asking me how many control words do I have in words. They are asking me how many, like size of the memory in words, size of the control memory in words, how many number of words, how many number of control words do I have. So each word is 26 bits, but I don't need to do this conversion, right? Total I will have 2 raised to power 10 control words, because this many address field I have. Each word is 26 bits, that is fine, but they are not asking me in bits. They are asking me how many words I have. I have 2 raised to power 10 words, that is 1024. So option A will be correct. So just be careful what are they asking exactly. That also you need to be careful about. Okay, so this is also a very good question. Okay, so like in what unit they are asking, this also you have to be very careful. Now let's solve this next question. A CPU has only 3 instructions, I1, I2, I3. Which of the following signals in time steps, this I1 is this, I2 is this, I3 is this, which use the following signals in clock cycle T1 to T5? Which of the following functions will generate the hardwired control signal for signal in? So like which of the logic functions? This is simple, right? This is just Boolean algebra. You can directly solve it. This is very simple, right? They have written in terms of what? In terms of instructions. So I will check in which in each instruction in which time zone my AN is common. So that I will check, right? So it's very simple, right? You can do it. It's just simple Boolean algebra. So AN is equals to IN should be here. Okay, in IN, in which time periods I have AN signal? In T1 time period I have AN signal, so I'll write here T1, or, and I have T3, right? T3 only at T3, T1 or T3. Okay, so log this T1 or T3, correct? So next what do I have? Or this is not I insert, this is I1. Now in instruction I2, do I have AN? Yes, I have AN here in T3. So it will be T3 into I2. In instruction I3, do I have AN? Yes, at T2 and T4 and T3. So T2, T3 and T4, T2, T3 and T4. This will be my instruction I3. Okay, so this is basically my logic family. So if I see T1 and T3, T1 and T3 is okay, T1 T3 is not present anywhere. Okay, actually one common thing I observed, that T3, right, it is present in all of them. So this T3 can be directly converted into, this will be T1 I1 plus I2 will be gone actually. Oh, I know I2 will be present, plus T3 or T2, T4, I3, because I don't care whatever instructions I have. T3 in T3 time period in third clock, the AN signal is always high. The AN signal is always high in T3 clock period. So it doesn't matter if T3 is on, right? This AN signal will always be high. If I make T3 higher, if I make T3 1, it won't care about the other bits. If T3 is on, that means I know AN is 1, right? I can understand from here as well. At every T3, I'm saying AN signal is always on. AN signal is always on. So if T3 is on, AN will automatically become on 1. Okay, so that's why this only becomes T3. How does it become? Like we do it like this. That here T3, I1 or I2 or I3. Only I have this 3 instructions, right? It doesn't care whichever instruction it is, it will always be on. That's why I1, I2, I3 is simply 1. Okay, I hope you understood this point. Now T1 I1 is present here. T2 I3 yes. T4 I3 yes. T4 I3 is present. T3 yes. T3 is also present. So option A will be correct. You can check the other options. Other options won't match. Here I have T1 T2 T3 I3. T1 T2 T3 I3 no, right? T1 is not here. T1 is not with I3. So this is gone. T1 T2 I1. T1 T2 no. T2 is not with I1. This is also gone. T1 T2 I2. T1 T2 I2 no. T1 is not with I2. Okay. T1 is not equal to I2. So all the options are gone. So simple, like it's simple Boolean algebra logic only. So basically I will just like show you an example what is happening in the hardware circuit. What is happening? So basically I have a control unit here, okay, and this is like a decoder circuit. So I will have instructions I1, I2, like this, I3, and then I will have the timing signals as well. Okay, T1, T2, T3. Now what it will do is it will give me the output. It will give me the output of what? A in will be here, then other logic, right? B in will be here. Each will have its own control signal, and this is what I am implementing. Control logic. I am implementing the control logic in hardware. This is hardware, right? So it is not programmed inside the lookup table. It is not there. So it will become very complex, because every time I have to like write this logic family, then decode, it will be very, very complex, right? Hardware will be very, very complex. That's why we generally avoid hardware unless and until we require very, very fast operation. Now we'll understand about this CPU design, right? CPU design. Like we have two things, two types of instruction set computer. One is reduced instruction set computer, another one is complex instruction set. This is just theoretical point. Okay, this is just theoretical point. That's it. In reduced instruction set architecture, we have fewer instructions focused on simplicity. As the name suggests, reduced. In complex, we will have larger instruction set for complex operation. Here, our length of the instruction will be fixed. Whatever we have studied this RISC, right? Where our length of instruction was fixed. Our opcode was variable, but length of instruction will be fixed. That's why it is easy. Here, the length of instruction will be variable. Then the decoding of the instruction, right, will be more difficult. Complex instruction that may involve multiple operations. So the decoding of the instructions will be very, very difficult. Just like index scaling, we can have index scaling and base address register, all those things, right? We can implement in complex instruction set architecture. It has limited addressing mode. It cannot support all the addressing mode because it is very simple. It's simple and straightforward. We cannot use all the addressing mode. It supports various addressing modes like index scaling and all those things. Okay. It is easier to implement using a hardware control unit, because as the instruction set is easy, the decoding logic is also very easy. Here, the decoding logic is easy. So if the decoding logic is easy, that means like it will be easier to implement in hardware. But as the decoding logic is easy, we don't implement in hardware control unit for complex set instruction CISC. We implement it in microprogramming. Okay, microprogram control unit typically executes one instruction per cycle, may require multiple cycles per instruction, because as the instruction itself is very, very difficult to understand, it needs to decode, and there can be multiple things in one instruction. There can be multiple micro operations. Okay, arithmetic operations are register to register only. It allows register to memory and memory to register arithmetic operations. This is the difference. This theoretical point you should know for placements and as well as gate. Larger number of registers are available, fewer registers are available, because mainly we'll focus on more memory and other things. Highly efficient for pipelining. What do you mean by pipelining? We'll understand this in the next lecture. What is pipelining? Don't worry about this right now. Okay. So there are a few theoretical points, few theoretical questions about CISC and RISC. The main difference between CISC and RISC is /R, that a RISC processor typically has fewer instructions. Yes, the full form is reduced instruction set. So obviously it will have fewer instructions. Correct. Has fewer addressing modes. Yes, it has fewer instructions, fewer addressing modes. Like a CISC supports complex addressing modes. Has more registers? Yes, it has more registers for faster operation, because mainly we allow only register to register computations. We allow mainly register computation. Okay, is easier to implement using hardwired logic. Yeah, yes. Our RISC processor is easier to implement using hardware logic. Why? Because decoding logic is decoding logic is simpler. Decoding logic decoding logic is simple. So option D will be correct. All the options will be correct. A, B, C, D. Now let's solve the last question of today's lecture. So we have this question. Consider the following processor design characteristics. Register to register arithmetic operations only. Fixed length instruction format. Hardwired control unit. So it is a characteristics of RISC processor. Which of the following are above characteristics of RISC processors? All of these are characteristics of RISC processor, right? So 1, 2 and 3, all of these will be correct. Okay, option D. So these type of question can come on gate and placements, be a bit of theoretical concept about CISC and RISC processing. Okay, that's about it about control unit and RISC and CISC processor. I hope you have enjoyed the control unit. We will have finished the control unit. Next, a very important topic will come, that is pipelining. So don't skip it. Be fully attentive on that, because you can expect question on placements and on gate from pipelining. It is a very, very important topic. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.